Hello everybody, this is Gauranj Kapoor from TheMathsGeek. This is my first video on this channel and I am very excited to present my ideas. Let's dive right into it. This is my first video on the generalization of an interesting pattern in the Fibonacci sequence. So let's dive right into it. Just as a refresher, well, what is the Fibonacci sequence? One of the most important and exciting sequences in mathematics, the Fibonacci sequence, surely known to any schoolboy, runs as follows: 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, and so on. Fun fact: 1 and 144 are the only perfect squares in the Fibonacci sequence. The Fibonacci numbers follow this rule: Fn equals Fn minus 1 plus Fn minus 2. So the nth Fibonacci number is the sum of the two previous Fibonacci numbers. The ratio of two Fibonacci numbers converges to the irrational number golden ratio, or pi. I must mention two consecutive Fibonacci numbers. Phi is the positive root of the quadratic polynomial x square minus x minus 1. So if you input phi into this polynomial x square minus x minus 1, what you basically get as your output is 0. And phi is 1 plus the square root of 5 all over 2. Johannes Kepler was the person to prove that the ratio of two consecutive Fibonacci numbers converges to phi. You must have heard him from his famous Kepler's laws of planetary motion. The proposition which I am going to present in this video is as follows. Let Q of n be a sequence defined from 0 to infinity which obeys the rule. Q of n equals the sum as I goes from n minus k to n minus 1 of q sub I, where k is a positive integer and is greater than 1. Right? Because if it's equal to 1, then there's no fun. So what we are trying to convey is that all sequences which belong to our category must obey the rule that the nth term of our sequence is the sum of k previous terms in the sequence. Now I am going to let alpha denote the limit as I would go to infinity of q sub I over q sub I minus 1. So basically alpha is the ratio of two consecutive numbers in our sequence as they get larger and larger. Now I'm going to define a polynomial g of x as x to the k minus the sum as I goes from 0 to k minus 1 of x to the I. So basically our polynomial g of x is x to the k minus x to the k minus 1 minus x to the k minus 2 and so on till minus 1. Now by observation we find that g of alpha equals 0. This implies that alpha is a root of a polynomial with integer coefficients, which thus implies that alpha is algebraic. Now, lemma: alpha is irrational for all k. Proof: this is a proof by reductio ad absurdum via the Rational Roots Theorem. Now let's go ahead and verify some cases of our proposition and lemma, beginning with the base case k equals 2. Right, so we get the Fibonacci sequence where Fn equals Fn minus 1 plus Fn minus 2. Dividing both sides by Fn minus 1, we obtain Fn by Fn minus 1 equals 1 plus Fn minus 2 by Fn minus 1. Now letting Fn over Fn minus 1 equal beta and assuming that at infinity the ratio is constant no matter how many steps you go forward or backward, we get beta equals 1 plus 1 over beta. Since if we had Fn minus 1 over Fn minus 2, we would have beta. Therefore, Fn minus 2 over Fn minus 1 is 1 over beta. Now multiplying both sides of this equation by beta and bringing everything to the left hand side, we get this quadratic. Beta square minus beta minus 1 equals 0. Since this polynomial is of the form g of x with degree 2, the proposition holds true for k equals 2. Also, as you may have observed, the root of this polynomial is phi, which is an irrational number, thus our lemma is true. Refresher, phi is 1 plus the square root of 5 whole over 2. Verification for k equals a 3. We're going to get a Fibonacci sequence, so get your Fibonacci seatbelts on. The nth Fibonacci number is equal to the sum of the three previous Fibonacci numbers. Again, dividing both sides by the n minus 1 Fibonacci number, we get Tn over Tn minus 1 equals 1 plus Tn minus 2 by Tn minus 1 plus Tn minus 3 by Tn minus 1. Again, assuming the ratio to be constant, we get n equals 1 plus 1 over n plus 1 over Tn minus 1 by Tn minus 3, since a number is the reciprocal of its reciprocal. Now, using our recursive formula that the nth Fibonacci number is the sum of the three previous ones, we can write Tn minus 1 as Tn minus 2 plus Tn minus 3 plus Tn minus 4. Right? So now you notice that in the denominator of the third fraction which constitutes our sum, we have Tn minus 2 over Tn minus 3, which is nothing but n itself. Tn minus 3 over Tn minus 3 cancels out to be 1, and Tn minus 4 over Tn minus 3, as you may have guessed, is 1 over n. So we end up with this: n equals 1 plus 1 over n plus 1 over n plus 1 plus 1 over n. Now I'm going to multiply both sides by n times n plus 1 over n, also known as n square plus n plus 1. We get n cubed plus n square plus n equals n square plus n plus 1 plus n plus 1 over n plus n. Cancelling the n squared and the n's from both the sides, we get, so this n squared goes out with this n squared, and this n goes out with that n beside the n squared in our RHS, sorry. Yeah, so now we get n cubed equals 2n plus 2 plus 1 over n. Multiplying both sides by n, we get n to the fourth equals 2n squared plus 2n plus 1. Now, bringing everything to the LHS, we obtain n to the fourth minus 2n squared minus 2n minus 1 equals 0. Now, you might have said, well, this has become even more challenging because it looks like we have to tackle a biquadratic over here. Don't worry, but this is gonna factor very nicely. How? Well, let's see. Now, n to the 4 minus 1, you can factorize this using the algebraic identity a square minus b square equals a plus b times a minus b. So this factorizes out into n squared plus 1 times n square minus 1. Again, n square minus 1 can be written as n plus 1 times n minus 1. So that part is sorted out. Let's focus on negative 2n squared, negative 2n. The only things common are minus 2n, and what will be left inside is n plus 1. So now, as you can notice, by grouping the first and last and the two middle terms, we have an n plus 1 common out of the whole equation. So we write that as n plus 1 times the inside bracket, which is n minus 1 times n square plus 1 minus 2n equals 0. Now, well, let's see how we can improve on this. We can write that only the inner bracket has to equal 0. Why? Well, since n is a natural number, if since n is a positive integer, sorry, since n is a positive real number, we obtain that this inner bracket must equal 0. Since if n plus 1 would have equaled 0, then we would obtain that n is negative 1, which is not possible in our case. We get n cubed minus n squared plus n minus 1 minus 2n equals 0. And now combining the two n terms, we get n cubed minus n squared minus n minus 1 equals 0. And as you may have noticed already, this is of the form g of x with degree 3. And hence our proposition holds. The lemma is also true since the root of the above polynomial is an irrational number. You wanna see what it is? Here. Whoa! 1 plus cube root of 19 plus 3 times root 33 plus the cube root of 19 minus 3 times root 33 all over 3. That's surely irrational, isn't it? Right, so these were the demonstrations, and now let's move on to proving our lemma. Lemma. Alpha is irrational for all k. Proof. Now, since alpha is a 0 of the polynomial, we want to set x to the k minus x to the k minus 1 minus x to the k minus 2 and so on to equal 0. When written in the standard form as an x to the n plus an minus 1 x to the n minus 1 plus a naught equals 0, the polynomial has an equal negative 1, that's the leading coefficient, and a naught an equal positive 1 and a naught, which is a constant term, equal 1. Now we're going to use our tool here, the rational roots theorem. By the rational roots theorem, if a rational root p over q exists for the polynomial, then p divides a sub a naught and q divides a n. That is to say, p divides negative 1 and q divides 1. Now a proof of this will be linked in the description below, and here is a photo of the theorem. Right. Thus, the only possible rational zeros of the polynomial can be negative 1 over 1 or 1 over 1, namely 1 or negative 1. Similar reasoning, since alpha is a positive real number, we must have it to be greater than 0. Therefore, the only possible value of alpha is 1. But, well, we can clearly notice that plugging 1 into our original gfx equation will not give us 0 in any case. Well, the only case it would give us 0 was when k would equal 1, and we've already laid a constraint that k has to be greater than 1. Therefore, any polynomial of this type cannot have any rational zeros. Well, we know that alpha is a zero of this polynomial, which simply implies that alpha is irrational. And as all mathematicians end their proof, square a box or QED. Thank you for watching this video. Hope you all liked it. Please don't forget sharing and subscribing. Thank you. Goodbye. See you next time. This is Gauransh from MathsGeek signing off.